Hello, my name is Ender Jaska, and together with my teammates Jacob Porter, Peyton Nguyen, and Timothy Bang, we looked at the Myhill-Nerode theorem. So what is the Myhill-Nerode theorem? It was proven by John Myhill and Anil Nerode in 1958 at the University of Chicago, and it determines whether a language L is regular. It also implies the existence of a unique minimal DFA for every regular language, and this can be found through the proof by exhaustion or proof by cases method. So before we get into the theorem, we have to talk about distinguishing extensions. So the definition says that given a language L and a pair of strings x and y, a distinguishing extension is a string z such that exactly one of xz and yz belongs in L. If such a z exists, then x and y can be said to be distinguishable. So take a look at the following potential portions of a DFA here. If strings x and y lead to the same state, then it's fair to say that xz and yz will also lead to the same state. However, if x and y lead to two different states, then we don't know where xz or yz will lead. They could lead to the same state or they could lead to different states. So the key diagram we're focusing here on is the center case. If xz and yz lead to different states, then x and y should also lead to different states. In this case, z is a distinguishing extension for x and y are then distinguishable. So after talking about distinguishing extensions, we can define a relation um, between x and y if and only if there are no distinguishing extensions for them. We can say that x and y are indistinguishable and they're part of the same equivalence class. They're equal in our sense if they have no distinguishing extension. The Myhill-Nerode theorem says that a language L is regular if and only if this relation has a finite number of equivalence classes.
So now let's do an example with proof by exhaustion. So let's prove that the given language is regular. So let's start out with the empty string and let it be the first member of our first equivalence class. And let's compare with 0. Now, there's no string z that we could have that would make it so that the empty string and z and 0 and z uh, have it where one is in the language, one is not. If you add any number of zeros and ones and zeros and ones, then both can either fall in or fall out of the language. So from this, we can say that since the empty string and 0 are not distinguishable, they're both in the same equivalence class. And this is also true for any number of zeros. Now, when we compare 1 and the empty string, we could add strings such as 0, and which would make it the case where the empty string and z and 1 and z, where z is 0, would have it where 1 is in the language and 1 is not. So from this, we can say that 1 is distinguishable, and that it must belong to a different second equivalence class. And this and again, from the first part, this falls for any number of ones too. And then finally, there's a third equivalence class, which is unaccepted strings. Uh, and then finally, this gives us a total of 3 equivalence classes from the Myhill-Nerode theorem, which means that the language must be regular. And additionally, since these 3 classes corresponds to states of the minimal DFA for the language L. Okay, now from this, we also have a corollary, an example too. So if the equivalence relation has an infinite number of equivalence classes, then the language L must not be regular. So for an example, if you look at the given language, we'll try to prove that it's not regular. So per the corollary, we should find an infinite set of distinguishable pairs of strings that are in the language L. So let S be any number of zeros. So for each pair of 0i, 0k in our set, with I being less than k, we have a distinguishing extension 1i. This can be seen as 0i, 1i is in the language L, but 0k, 1i is not. And what this means is we have an infinite number of distinguishable strings, and therefore the equivalence relation must have an infinite number of equivalence classes. And then, this implies, that we can find a minimization of DFA. So, as a result, there exists a minimal DFA for any regular language L, and the idea being that we should be able to reduce any existing DFA for any regular language to its minimal form, and that minimizing DFA is important because it allows us to reduce both the time complexity and the space complexity of automata. And we do this through a table filling method. And here are the steps for our table filling method, but we will use these in our upcoming examples.
So for our first example, we're going to minimize this DFA. So for step 1, we want to create a table that constructs all the pairs of states in the DFA. And we only want to use the lower triangular part of the table because we don't really care about the direction of like the two states. So for example, we don't really care if it's like AB versus BA. We just care if the two states, if one of them are final, which we'll explain more in the next step. So yeah, in the next step, for all the pairs in the table, we want to mark the entry if exactly one of the pairs is a final state. So as we can see here, A and B, B is a final state. And like I mentioned earlier, we don't really care about whether like A is a final state and B is not, because this is just considered whether the two, just the two pairs, if one of them are final. And then for step 3, after one iteration, we're going to go through each unmarked cell and mark it if the transition state for every action for a pair of states is currently marked on the table. So in other words, this just means if the transition state for every action, if at least one of them has the pattern where one is a final state and one is not, then we've marked that cell. And then we just continue until we can no longer mark a cell. And then we want to combine all the unmarked states or unmarked pairs into a state. So as we can see in the previous table, BC and DE are unmarked states. So we can merge these two and create a final minimized DFA, which would be shown right here.
So now we just move into another example with a different DFA picture here. So with the first step, again, we just create the table and construct all the pairs of the states in the DFA. And then the second step is to see in the pairs if we have exactly one final state. And if we do, then we mark that section. Now in the next state, or in the next step, we are looking at the unmarked cells. For example, let's take the unmarked cell DB. Now we have for D, if we are given an input 0, then it leads to B. If we give B an input 0, then it also leads to B. However, we see that we ignore the cell BB in our table. Now we do the same for the inputs 1 for each. For D, it leads to E, and then for B, given a 1, it leads to D. Now we look at the cell ED, and when we look at cell ED, we saw that it was previously marked. Therefore, we are going to mark the section DB, and we do this for all pairs. We continue. This is our second iteration showing the cells that we marked. And then we simply repeat until we can no longer mark any cells. This allows us to see that AC, the unmarked pair, is the states that we have to combine. And it gives us a minimal DFA pictured here.
So for a summary of what we've talked about, first thing is that distinguishing extensions are a way to help differentiate two strings into equivalence classes. And then also from the Myhill Nerode theorem, it helps us determine whether a language is regular based on the number of equivalence classes that it has. And what the theorem also implies is that there is a minimal DFA for any language L, and that this minimization of a DFA is done through the table filling method. And this is important because it helps us to, reduce the time and space complexity. Thank you for watching.